Okay, so I hope everyone can hear me good. I'll try to speak as loud as I can. So what I will present today is the work that I did here in my secondment in the HAW. So I was working in the biology department and I was doing some toxicological tests on Daphnia magna. So the main aim of it was to evaluate the toxicity of gadolinium and lanthanum. So I will give you an overview of what the presentation will be about. So it will be focused on the 7-day test on Daphnia magna. And I will start with the justification, then the test design, the exposure conditions, the data analysis, the results. I will have some discussion about my results and then the relevance of the test, and then go on the conclusions. So the justification is at the moment we have 2 types of standardized tests, as it was mentioned already today. We have for Daphnia the acute test, which is very simple. It's a very short test and is very highly cost effective. And we have also the standardized chronic test, which is more relevant for other subchronic or chronic biological endpoints. It's multi-generational because Daphnias reproduce very rapidly. But one disadvantage is that it's very time consuming. So for this, we came up with doing something not standardized, which we call subchronic test. And this is a compromise between the acute and chronic test. So we could measure more endpoints than the acute test. And it was a bit more it was not a bit, it was more time efficient than the chronic test because it was only 1 week, so 7 days, compared to the 21 days chronic test. So here I have a table with the different test designs of each test. So for the acute, this one is 48 hours, the chronic 21 days, and the subchronic, we set it to 7 days of exposure. So one of the other differences is the feeding. So for the acute, normally the Daphnias are not fed. For the 21 days, they are fed either daily or at least 3 times a week. As for the subchronic, we were feeding them every day, daily. And something else was, some other difference was the format. So normally the acute test is static. So this means that the media is not renewed. And then for the chronic, you have to renew the media either 3 times a week, or it can also have the option of have a flow-through test. For this case, the chronic, we kept it static, so we did not change the media during the whole 7 days. And then for the responses that you can measure, we have for the acute, normally it's only measured either the mortality or the mobility. For the chronic test, this is more focused on the reproduction, but of course you can also measure the mortality and also the growth as endpoint. So we measure the mortality, some endpoints of the reproduction, and also the growth. So our test design, we did the test on Daphnia magna, and we kept the validity criteria from the standard test, which is the control mortality has to be less than 20%. As I mentioned, the test was static, so we did not renew the media, and we did daily feeding with Rhaphidocelis subcapitata. We had 3 replicates with 5 individuals, and we did multiple repetitions to have at least 4 replicates for mortality each day. So this meant we did 10 tests with lanthanum and 13 tests with gadolinium. The endpoints that we measure and that I will present are the mortality, the feeding rate, the growth inhibition, and the maturation of the Daphnids. So our exposure conditions were 21 degrees with 16.8 like that photo period. We fixed the pH to 6.8. We used the media element, which is also standard for the other tests, but we removed the ADTA. And the concentrations that we used for lanthanum were, we used the minimum of 5 concentrations. And for gadolinium, we have this plus 2 more concentrations, and I will explain later why. So first endpoint, which is the mortality. So I will express this as the endpoint with the LC50, so the leader concentration affecting the 50%. And this was calculated from the pool mortality of all the experiments that we did. I fit the data into dose response model, which is a 2-parameter log logistic. And I fixed the upper limit to 1 and the lower limit to 0. So I treated the data as binomial because either the Daphnia are alive or dead. There is no half dead or half alive. So it's either one or the other. So also, which was something that was very good, that we did not have to correct the data to mortality. So we fixed to 0 because our control mortality was always below 5%, except for the lanthanum on day 7. So then our results, as you can see here in this graph, this is the day 2 is C50, which is the value estimated was 5.42 milligrams per liter. Then for the day 3, it decreased to 4.49. For day 4, it was 3.26. For day 5, 2.73. For day 6, 2.29. And finally, last day, the 7, 2.08. As you can see, the estimates were decreasing, and also we will have a better looking curve as the days increase. So then now for gadolinium, we have for the LC50 of the 2 days was 3.67. Then for day 3, 2.33, 1.89, 1.55, 1.45, and lastly 1.38. So as you can see, for the both elements, the LC50 was decreasing with increasing day, and also the estimates the confidence intervals, this is the 2 lines that you can see around the estimates, were also decreasing because the data was improving for the mortality. So then what I wanted to do was a comparison between the LC50s that I obtained for every day. So then for this, I used a test, which is the interval ratio test, confidence interval ratio test, which there the new hypothesis that the true difference in LC50 values is not equal to 0. So then if the confidence intervals contain 1, this means that we reject the null hypothesis. And for this, even if the values were decreasing, this only means that the days 2 and 7 values are significantly different. From day 3 to 6, those values, even if they were decreasing, they were not significantly different. And this was the same for lanthanum and gadolinium. So then our next endpoint was the growth inhibition. So for this, we measured the distance of the Daphnia, so from their eye to the end of the tail. And I compared the treatments to the control. For this, I used the Bonferroni adjusted t-test, which is a correction for multiple comparisons. And I fit the data to obtain an EC10 and EC20. I used the 4-parameter brain cushions, and I fixed the lower limit. Well, I didn't fix it. This model has the fixed lower limit to 0. Here we can see the growth inhibition. You can see that from the value of 1 milligram per liter, the growth was significantly inhibited compared to the control. And something that is very interesting is that for lanthanum, this actually works now. There seems to be some stimulation on the growth, which is not so obvious for the gadolinium. So then for this reason, we wonder if there was maybe a hermetic effect. So as I was explaining in the morning, this is when there is some stimulation compared to the control. So this has been studied on rare elements that at lower concentrations, they can actually cause some more growth on some species. So for this, I fitted the Brent-Cousins model, which accounts for hormesis. Here, the lower limit is fixed at 0. And here are some parameters obtained for this model that I will get into detail. First, we have the B and the E, which is the slope, the concentration E. They are not relevant to this model, but then this just that you know what they mean. Then we have the D, which is the upper limit of the model. In this case, it was the 2.54, which is the highest point of the measurements. And we have the F, which is the one that we are interested about, because the higher the estimate of the F, this means the higher the hormesis effect is. But as you can also see, we have here some p-value, and this is a statistical comparison of the estimate to 0. So then if the value is significantly different from 0, the null hypothesis in this case will be that there is no hormesis effect. And in this case, because we have a p-value that is not significant, this means that we cannot reject the null hypothesis, which means that even if we can see some hormesis, it's actually not so much that we can say it's different from 0. So in this case, it's not so relevant for this data, but for other models, it could be if we have, as this can affect the estimation of the EC50, and we then, this doesn't work. Estimate a wrong value, not wrong, but just underestimation. So then I obtained an EC10 and EC20, which 1.38 and 2.7. So here I want to say that this is not, this is calculated between the upper limit and to 0. So there is actually not like the point where the growth was inhibit 50%, because we didn't have, let me rephrase it. Yeah, the 10 and 20% reduction from the highest limit of the model. Yeah. Then the same for the gadolinium, as we saw that if lanthanum seemed to have a bigger hormesis, we can see that 0.75. This is lower, and it's also not significant, which means that there is no hormesis. The hormesis effect is not so big also in gadolinium. So then these are the estimates I calculated for the EC10 and the EC20 related to the model that was fitted. And then our next endpoint was the feeding rate. For this, we measured the fluorescence at the end of the test, and we assumed the finest numbers of cells based on the numbers of cells we were adding daily. So with this, we could calculate the cells consumed. So this is the sum of the cells add minus the cells measured at the end. With this, we could calculate the feeding rate, which is the cells consumed divided by the number of daphnias alive per day. And to compare the data, in this case, I used a Tukey test, which corrects the family-wise error rate. This means that when you have multiple comparisons, you increase the probability of getting a type 1 error. This is a false positive, so you need to correct your p-values. And it's also a better method if you have unequal sample sizes. In this case, you can see that for lanthanum, for the control, I have 18. And then for the highest concentrations where the daphnids were alive, I have only 12 samples. So then for gadolinium, it was something similar. For my control, I have 29 samples, but then for the 2.5, only 8. So then this is the results represented and percentage of the feeding rate. So as you can see, also the feeding is decreased with increasing concentration. And again, where we can see that there is a significantly decrease from the control. And lanthanum occurs at 1, and for gadolinium at 0.75. And what is interesting here is that this red line indicates the point where the feeding rate is 0%. So how can we have a negative feeding rate if it could not be possible? And this might have been due to other problems that we had during the test. So one of the assumption is that the daphnids were feeding less, which caused the numbers of cells of algae available. So increase the number of cells available, which then made them grow more. So then we actually ended with more cells available than what they could eat. So then for this reason, we get negative values for the feeding. Then we wanted to measure the correlation to see if there was a relation between the growth and the feeding. So if they are growing less, they're also feeding less, or to see if there was a correlation. So then we got this linear regression for the data, and the closer the R square is to 1, the higher the correlation is. So we can see that for lanthanum, we have an R square of 0.65, which is not so good. There is some correlation, but we don't have enough data points to actually say if there is or not one. This blue dotted lines is the confidence intervals of the linear regression. And then for gadolinium, we can see that the data is a bit more dispersed. So we actually get a lower R square, which means it will be less possible that the size and the feeding are correlated, which is very interesting. So then our last endpoint is the maturity. So we count the maturity as the number of daphnids that could produce eggs. This is when we say they were mature. So we can see here, this is an example of what we consider a not mature daphnia, and then one with eggs, which is one that has reached maturity. So we calculated from the initial numbers of daphnia, and we excluded the mortality from the calculation. So how many in total from the daphnias in the beginning could reach maturity at the end. So for this, I fitted 2 different models for the 2 elements because they were the best fit. But again, the lower limit was fixed at 0. So then here you can see the percentage of maturity. So for both tests, the control, the number that reached maturity was about 30%, and it also decreased with increasing concentration. So we can see again that in this case, between 1.75 and 2.5 was the point where they were not reaching maturity at all. So then we fitted this viable model, which was the best fit for our data. And then here again, we have the similar parameters as before. So the B is the slope, the D is our upper limit, and then we have the E, which is interesting because this is the EC50 we obtain. And this is again in relation to the upper and the lower limit of the model. So then this is an estimate, that the model just give you. And then I wanted to also know where the 10% and the 20% reduction was of the model. So for this, it was 0.45 and 0.54 milligrams per liter. And then for the gadolinium, we got something similar, that the EC50 of the model is 0.68. And then the 10% reduction and the 20 was at 0.42 milligrams per liter and 50 milligrams per liter. So now about the test, what are the future prospects for it? So we had some problems with knowing what are the actually effects of the algae we use for food. And this is because we just made the assumption over the quantity of algae. So we do not know how much algae was present every day. We only measure it at the end of the test. And with this, we do not know exactly if it it's actually growing during the week that we are adding it during the test. And then also we had some problems because the algae will agglomerate over the days. So we don't know if this agglomeration caused that the daphnids could not feed on it. So are they not eating because they are affected by the element, or are they not feeding because they are not able to eat this algae that is in big clumps? So also we can then in the future focus a bit more on the environmental relevant concentrations. So on lower concentrations to see if we got some effects, maybe not on mortality, but then definitely for other endpoints like in the reproduction. So then some advantages of the test, because this was not in standard. We were really happy that it worked. So then we could, just as the other tests, we could measure the mortality, the feeding rate, the growth, and even from the reproduction, we only calculated the percentage of maturity. But of course, we do not know if the maturity will never arrive, or it was only delay, or the number of offsprings that they will be able to produce. This will only be possible to determine with a longer test, so with a chronic, which takes longer days and effort. So then this was already mentioned, but why is this relevant? Of course, we want to maintain like simple tests, but still want to adapt them so they are more relevant to the environment. So this is useful for the risk assessment. Well, you already heard today about the predicted no effect concentrations, which are calculated with the estimates that we obtain from tests. And then these are divided by the assessment factor, which are determined by the uncertainty related to the data available. So as mentioned, they can be from 1 to 1,000. So we want to be conservative to that the organisms in the environment are protected. So then from the estimates obtained from this test, we can see that there depending on the endpoint that is looked at, we can obtain different estimates that go from 2.8, and then I think for lanthanum 2.8 to the lowest, which was 0.44. And then depending on which one it is used is what is the value that in the environment will be okay to have, without causing any negative effects. So then as a conclusion, we see that gadolinium seems to have a higher toxicity than lanthanum. So this was assumed because we had a lower LC50, which means higher toxicity. And then, so we also saw that from the standard test, we got the 48 hours LC50, which were significantly higher than the one we obtained for 7 days, which is interesting if we think that the 48 is the one that we use for the risk assessment. And then also we saw that there was some reduction in feeding and maturity on the daphnids, which is interesting to see in such short period of time, which was 7 days. So then that was my presentation, and I thank you for your attention, and I hope it was clear.
Thank you very much, Edith. I don't know if you have any questions for
Not in the football.
Oh, good. No questions? Okay, so maybe I will start to prepare a Chantal's presentation.